Hello and welcome. What does a skeleton say before eating? Bon appetit! In this video, we're going to look at parametric equations. Let's get started. Parametric equations are another way of describing curves in the xy plane. As an example, here are two parametric equations, a set of parametric equations. X equals t squared and y equals t plus 1. Notice that it's two equations, not just one equation, that are going to create this curve. Each value of t, when you plug it into the set of parametric equations, gives you an x and a y coordinate. The first equation gives you the x coordinate, and the second equation gives you a y coordinate. So let's take this set of parametric equations and plot a few points. The way we can do that is by making a little table. So we'll input a bunch of t values. T goes from -3 here to 3. And we'll figure out what the corresponding x and y values are in the other columns. Excuse me. So when t is equal to -3, what is x equal to? If you said 9, then that's correct. What about y? What's y equal to? If you said -2, that's correct. So you just take the value t of equals -3 and plug it into each equation to figure out what the x coordinate and the y coordinate are. So each value of t corresponds with a point in the xy plane. What about for t equals -2? What's your x and your y? If you said 4 and -1, then that would be correct. Now you can do this for all these other t values, and this is what you would get for the xy pairs. Then you could take these xy pairs and plot them on a coordinate system. So here's a coordinate system in figure 1. Let's take those xy pairs that we got for those various t values, put them up on the coordinate system. So here at 9, -2, that was the t equals -3 point. Here at 4, -1, this is the t equals -2 point, and so on. And then what we could do is imagine, there's probably a t equals -2.5 point somewhere in the middle of the t equals -2 and t equals -3 point. So there are more points on the graph. We just haven't found them yet because we haven't plugged in those t values. But by drawing these points, we can get a sense of what the curve is going to look like. It looks like some kind of parabola that's opening to the right with a vertex of 0, 1. And even more than that, we can say what the direction of the curve is as we increase the value of t. As t increases, we're moving along the curve to the left at first, and then as we cross through t equals 0, which is at 0, 1 on the xy plane, we're going to start moving to the right. So we can draw these arrows that represent the direction of increasing t. T you can think of as representing time. So if you imagine a particle in the xy plane, then as t is increasing, as time is increasing, the particle would move along this curve in the direction of those arrows. So that's what the graph of that set of parametric equations would look like. What would happen if we restricted the parameter interval, which is the interval of t, from t goes from 0 to 2, including 0 but not including 2? Well, what that's going to do is just take a little piece of the graph that we were just looking at and only restrict the graph to that part of the original graph. So in figure 2, we have a blank xy plane again, xy coordinate system. And when t is equal to 0, we're here at 0, 1. When t is equal to 2, we're at 4, 3. Now I'm putting a filled-in dot at t equals 0, so that the 0, 1 point, because t could equal to 0 on this parameter interval. And then an open dot, so an open circle at 4, 3, in other words, at the t equals 2 point, because we don't have equality for t equals 2. T equals 2 is not really going to be a point on this graph with this restricted parameter interval. I guess I forgot to mention, t is the parameter. The parameter is t. So go back in there and insert a little head popping in that says, t is the parameter. All right. So then you're just going to draw the piece of the graph that goes from t equals 0 to t equals 2. And you'll want to draw your arrows to represent the motion, the direction of motion. So let's take a look at another set, the same set of parametric equations, and notice that we can turn them into a Cartesian equation. Let me come over to the notes. So we could have turned the parametric equations x equals t squared and y equals t plus 1 into a Cartesian equation. Cartesian just meaning in terms of x, y only. This is in terms of x, y. We could do that by eliminating the parameter t. Now, what we could do, one way of doing that for this set of parametric equations, and it's different for each set of parametric equations, is we could solve the second equation for t in terms of y, and then replace the t out in the other equation, so that we'll just get an equation that has x's and y's in it. Taking the second equation, if we subtract the 1 to the left and then switch the sides around, we get t equals y minus 1. Again, this is coming from that second equation, just solving it for y, or for t. And then in the first equation, instead of x equals t squared, we can write x equals y minus 1 squared. So we're just replacing out the t in the first equation with y minus 1. So we get x equals y minus 1. That's a Cartesian equation. That's an equation that's only in terms of x and y. Notice that it's a familiar Cartesian equation. It's the equation of a parabola that's opening to the right with a vertex of 0, 1. It's shifted up by 1. And that's exactly the curve that we got from when we plotted our points. Now, getting a Cartesian equation by eliminating the parameter can definitely help us identify the path of the curve. Like if we eliminated the t and we got this Cartesian equation, we could say, I know exactly what kind of a path that the parametric equations are going to follow if they're graphed. But eliminating the parameter is not always possible. Like the example that's given is x equals t minus ln t and y equals t squared plus sine t. If you try to solve either of these equations for t, you'll quickly run into problems. These just cannot be solved for t using the elementary functions. So in this case, we would be stuck. We would only be able to write this kind of a curve using parametric equations, which says actually something. It says that parametric equations are actually more powerful than Cartesian equations. You can draw any Cartesian equation as a set of parametric equations, but you can't always write every parametric equation set as a Cartesian equation. So parametric equations are going to open the door to even more different kinds of curves in the xy plane. This is especially true when you go on to Calculus 3, where you're going to look at three-dimensional curves. And when you want to represent a three-dimensional curve, the best way to represent it, if it's going to be a curve, is going to be using a parameter. So using some kind of single parameter to represent that single dimension of the curve. And if you have 3 coordinates for every single point in that curve, you're going to have 3 equations. Each equation will give you one of those 3 coordinates, 3 dimensions. So extending into 3D, you're going to need parametric equations to be able to do that. Thanks for watching this video, and see you in the next one.